So let's begin this class. Right. So in this fractal, we had in the previous class started looking at uh, concepts related to representation learning in general, and we specifically looked at one, sort of interesting technique of unsupervised pre-training, which is allowing researchers or any person who's developing a model to train a model uh, without having to use any of the labels. At least pre-train a model and give a proper initialization to a model without having to use any of the supervised labels as such. And it was observed that it was working, um, to improve at least in those days, whatever the state-of-the-art results were, it was able to improve those results. And I'll just brush over the rough concepts again so that we can again come back to uh, the frame of mind that we were in the previous class. So the idea was that whenever you have a multi-layered model, you simply first, train layer-wise. You take the first layer, say W1, and whatever input it's getting, you will try to produce the same, embedding of a similar size in the output, sort of in an autoencoder manner. And then when you do that, the objective will be to reduce the difference between the input representation and the output values. So you're trying to reconstruct the same input. And we'll keep on training the given layer till we are able to get a good enough approximation of the given input. And once we do that, the understanding or the underlying assumption is that we are able to properly model maybe that particular, say, layer at least. And once you have done that, you can then freeze that particular layer and then move on to the next layer. And the idea is that whatever output is coming up from your input and your frozen layer goes to W2 as an input, and you try to reproduce this input again, and so on and so forth. This goes on till you have finished all the intermediate layers. Obviously, you don't do it for the classification layer because classification layer has to be trained for your ultimate task, that is classification in this case. Okay, and once you have done with all of these things, you've done. You can go back to your main network and do a fine tuning on your main task of classification. And as a result, you are actually starting from a very good initialization of all the other weights, and it was found that this was helping to improve the model performance significantly. We also briefly discussed about what was the general idea that researchers explored. Why this particular setup was working. One of them was that you're not caring about the global objective, and rather you're learning more about the structure of the individual, say, intermediate representations or individual inputs that you're getting. And as a result, while learning the structure, you would have learned some of the good factors of variations within each of these, say, intermediate inputs or even the actual input. And that factors that you've identified actually helps to better classify, or maybe helps to quickly converge your model to a better solution. And there are also other factors that might come into play. People had explored a lot, but what it did as a result is, before 2006, it was getting more and more hard to maybe train deep models using the limited data that was available in those days. Label data that was available in those days. This certainly provided, number one, a big breakthrough of how to improve your performance, or maybe train even a deep model with, say limited data that you have. But also another thing that did was that it brought in renewed interests into fields like, say, looking at initialization techniques or maybe better optimization techniques or some additional modules that can have a similar effect. Where you have some local versions. We'll see at least one or two such cases, which were, which happened because there was renewed interest in optimizing or initializing a network much better. Okay, right? So this is what we'll be discussing in this particular slide. This particular unsupervised pre-training technique, the researchers observed that it was working due to maybe because of, say, better initialization, or maybe it was acting as a good regularizer, or maybe it was performing a better it was allowing a better optimization to happen when you're finally going towards the fine-tuning process. And so all of these fields now suddenly drew a lot of interest from the researchers, and you basically came up with better initialization, better regulation technique, and better optimization techniques. In fact, now if you tell anyone about unsupervised pre-training, this is not the layer-wise pre-training is not something anyone will maybe do at the first time. I mean, in the first attempt, they will try some more recent unsupervised learning algorithms, like say you have SimCLR or other contrastive learning techniques to pre-train a model. In fact, even all of the large models that you see, large LLM models that you see, they also nowadays use some or the other sort of pre-training, unsupervised pre-training technique before you move on to your supervised task of performing one or the other task that is assigned to it. And because of this renewed interest, in general, it's considered this point in 2006 is considered as a point of revival of the deep learning uh, domain in general, where people were paying more attention because now you were able to solve even more complicated tasks with, say, whatever data or compute was available in those days. And obviously, after that, by the 2011s and 12s, you had access to better computing resources, as well as you had the ImageNet model and other larger data sets, labeled data sets started coming up. So overall, this field, reviving after. Right. So, as I said, we have now much better unsupervised initialization techniques. One very basic one, but which an approach that works extremely well is that suppose uh, you have been given a set of images and you want to train a classification model on that. You can do a super self-supervised training on it first by maybe simply rotating the image by some fixed angles, and say you rotate it by 0, 90 degree, 180 degree. And then what you do is that you pass that image to the model, but instead of predicting the class, you predict the rotation angle. So in a way, you're not using the labels that are provided to you. So it's still not, you'll not consider them as supervised because you're not using the labels for the task that was given. But it's more like a self-supervised setup where you created your own labels and then you're trying to learn these particular setup. And in the process, you're maybe getting a better idea or better representation of the images that are. So these techniques are more recent and they have been producing better results. Right? And this, as I mentioned, unsupervised learning techniques are now the norm for retaining many large models, including, say, the LLMs that we have. Okay, now obviously, when I say disadvantages, I'm talking about the disadvantage of the layer-wise pre-training method. As you would have already noticed that we took a simple training mechanism where we had a single model and we trained it for, say, 10 or 15 epochs or, say, 100 epochs, and we divided it into two stages. First stage is obviously your pre-training stage where you're doing a layer-wise thing. So in case of a large number of layers, you have just, increase the complexity of your training much that many fold because you're now training each individual layer in your deep neural network separately, and then again you're performing the fine tuning. So you're adding a lot of overhead onto this entire process. But then that was something in those days we were willing to do because we didn't have a better option. So, another thing that comes into play is that since you have um, come up with a new pre-training phase or set of pre-training phase, you'll have to choose some hyperparameters for this pre-training phase as well. And maybe the hyperparameters that you choose will be different from one layer from the other. Maybe an initial layer will have a lower loss anyways, it's because it's closer to the actual input, but a later layer will have accumulated all the losses from the all the errors from the previous layers as well. So at a later layer, you might need more training or more pre-training, and the hyperparameters learning rate, all of these may be different. So that adds on onto your entire training paradigm, and which makes it a much more complicated.
So one thing I want to know, like the hyperparameter is associated to the features or what?
Hyperparameter is associated with, so you have parameters like the weights that you learn for training a model, and hyperparameters are parameters of parameters. That's why it's hyperparameter. It means that some decisions like, say, learning rate, batch size, number of epochs to train, these are generally referred to as hyperparameters for your deep learning. So these are not exactly trainable parameters, but these are something that you can maybe run a grid search or maybe do trial and error to find out the best hyperparameter for your purpose.
Mm-hmm.
So it's these things. So generally those are referred to as hyperparameters.
It's parameter of parameter.
Parameter of parameter.
Okay.
Right? Right. So you're introducing a set of more hyperparameters, and another thing that comes into play is that since you have a pre-training phase before your final training phase or fine-tuning phase, there will be a delay between the hyperparameter that you propose for your first phase and when you get to finally see the result of those hyperparameter tuning. So you're doing some sort of pre-training in the first phase, and for those you might have chosen some parameters, but the final effect of this hyperparameter will not be directly clear during the first phase. It will only be clear when you have done the fine tuning in the second phase. So there's a long delay between whatever hyperparameter you're choosing for the first phase and when you actually get to see the effect of it during the second phase, whether the pre-training phase was good enough or not, that will only be clear once you have done the fine tuning and you're obtaining the results. So that's another delay that you're putting onto the training process. So that in cases where you have a large number of layers, that particular hyperparameter um, tuning or hyperparameter identification process becomes lengthy process. And obviously, when you're doing any sort of, say, unsupervised pre-training using 3D layer-based training, as you've already seen, we use a lot of decoders, right? We have a lot of encoders, which actually turns out to be the model layer itself. But if you look at it, we also are adding a decoder at every level, which we discard, by the way, at the end. But this is an additional computation that you are putting onto the model, some additional overheads you're adding onto the model, even though you discard it, but at least while training that pre-training phase, you are actually having to use this additional space, additional weights for these things, also the additional space required by the intermediate outputs for these particular training. So that is maybe another overhead that you're putting on top. So these are some of the disadvantages of your using a unsupervised pre-training method or layer-based 3D pre-training method. We'll briefly look at some immediate after effects of, say, this particular renewed interest in deep learning by looking at some new models or new, say, components of models that were proposed immediately after that. And the first thing that we can look at is one of the most basic changes in the autoencoder models that we have seen. I mean, we have briefly discussed about autoencoders, and we had seen that the idea was behind autoencoder was you have an encoder and a decoder, and the idea was to reconstruct the encode. And we have a similar setup for another type of autoencoder that is known as denoising autoencoder. And the idea behind this particular denoising autoencoder is that you will add some random noise to your input as well, okay, and then you pass it to your autoencoder, but the autoencoder should be able to reproduce the actual input. And this was found to serve multiple purposes. One of the basic purposes, obviously, your model will now become much more robust to, say, some sort of noise in your input. Maybe you have a noisy image, like in this cases, your photographic instrument may not be, or maybe because of the weather, the pictures are not very clear. So if you're introducing some noise into the uh, auto encoding process itself, then your model then gets more focused towards the actually good information and is able to maybe ignore some noisy features. And another thing that comes into play is that now you have a much better regulation because you are even much more now focused on the good features or the good representations. So this entire process will create a regulation where your say if you do it for the you use some sort of an autoencoder for your unsupervised uh, initialization process, it will shift your, say, parameters to a space where the parameters would be even much more robust to noisy. So roughly the same idea, you're getting a better regulation or maybe much more robustness towards noisy. And this was a follow-up on these particular set of strategies of using, say, autoencoders or, say, some other models for, say, unsupervised pre-training. Again, this is the general idea. And this, as you can see, this is roughly in that same era you have, say, in 2008, where you're having this problem. And you will see a lot of work that was happening right after this 2006 period. And this generally is the idea again. You have your image, you have added some noise into it, but you and you apply your auto encoder, you have an encoding set, you have a decoding set, and then finally you try to reconstruct back the original image. And in the
Like,
process, you are
sir, this adding of W as an error,
yes,
right? As a
yes,
noise. So
huh.
it's intentionally we are adding here.
Intentionally we are doing this.
So what is the impact of adding like noise for this prediction?
Impact of adding noise for this. So the thing is that when you're adding some noise onto this particular image,
Mm-hmm.
okay, if I use the normal autoencoder, what it will do, it will try to reproduce this noisy image only. Okay, but
Mm-hmm.
in your losses, what you'll do is that you'll get the loss between X, which is the actual input, not noisy input,
Mm-hmm.
and the reconstructed value. So your autoencoder learns to remove noise from the identify the noise and remove the noise from your given image. So in the
Okay.
process, what you're doing is you're forcing it to even more. I mean, put a better focus on the actual good part of your image or better features, so that it can ignore the noise.
Hence the adding of W will give him an idea where is a noise like that.
No, no. Adding of noise will not give you. Yeah, yeah. That's true. That's true. By adding the noise and while by forcing it to reconstruct the original X, you are
Mm-hmm.
teaching it to ignore the noisy part and focus more on the image part.
Mm-hmm. Because the
That.
previous noise are, I mean, the inbuilt noise are very less, so he is not
Uh,
able to distinguish like
yeah,
that.
yeah, yeah.
Okay.
And sir,
To make it more.
sorry, one question around the previous slide where we talked about delayed hyperparameter learning. Uh,
Yeah,
yeah, so
yeah.
in this, basically the hyperparameters are for the training part of it that we're talking about. The
Yes,
pre-training
yes, yes.
anyways is the best of what that
Pre-training.
the pre-training part we have
Yes.
already identified the best encoding.
No, no,
That,
no. See, that's what they're saying. No? So that's what is being mentioned. So when you're doing the pre-training phase, what is the ultimate judge of whether your pre-training phase worked or not? Your ultimate judge is what performance you're getting after the fine-tuning phase. Okay. Maybe you have optimized your reconstruction very well. You have gotten a very good reconstruction intermediate layers. But at the end, when you're looking at the testing performance of your module, your testing performance is not that good. Okay, after fine tuning. So there is a delay between your pre-training phase, then you have your normal training phase, then you test the final model, and then you find out that actually it's not improving that much. Let me go back and update the hyperparameter of the pre-training phase again, and let's see if there is any improvement. So that's why there's a long delay between these two steps.
got it, got it.
Right. And another idea that we'll briefly look at is dropout and drop connect. This is again in the realm of better representation learning only. And as the name suggests, dropout, drop connect by default do not be able to maybe differentiate between them just looking at their names. But if you look at this particular diagram, dropout tends to basically zero out some of the neurons that are present in a particular layer. Okay. And what it does indirectly is that it is forcing you to provide a good output without using some of the intermediate neurons. Okay. And if you force a network to do that, what it will do is that it will become much more robust in dealing with, say, situations where, say, a particular image, you have the same data, but maybe in a different region of your given image. Okay. I mean, ideally, you're not using a convolution network yet, but you're using a fully connected network. And in a fully connected layer, you provide the image as a single vector. Right? I hope that is not very far-fetched. This whenever you provide image to a single network, you provide that image, because images by default in at least in a 2D way, 2D format. It can also be in C3 dimension, but we are assuming the image to be in 2D format. But your 2D format image will not be able to be fed to a fully connected layer. So generally what you do is that you linearize that entire image. If you have a 32 cross 32 image, you convert it into 1024 size vector and you feed it to an input FC layer, which has some size. Now, what happens is that maybe some of the nodes that are present in a fully connected layer becomes very good at identifying, say, a particular type of feature. Maybe say 2, 3 pixels over here, which may be representing some edge. One of the nodes becomes very good at identifying that particular information. Okay. But what happens if, because of some reason, this particular feature is appearing somewhere much below? Okay. Even though it's still connected to all, it's a fully connected network, it's fully connected, but maybe we would want that not only a single node gets to have a good ability to identify a particular feature, but maybe multiple nodes has the same ability. So that if for some reason there is some disturbance in these set of in the pattern that I'm trying to identify, and my that main module or main node is not able to identify that particular feature, I have other modules that can still work. Okay, that's the general idea behind any sort of dropout waste mechanism, where you're explicitly deleting parts. I mean, and also one more thing to be noted: dropouts are generally done during training and not during testing, because during testing you want to have all the trained nodes in your given network. Okay. So this is a very famous paper by Hinton in 2012. Again, he's been contributing a lot, and so in 2012 he came up with the dropout strategy, which basically randomly drops or makes the activations of certain neurons to zero during training iteration. And basically then what ends up happening is that you have a smaller subnetwork during each, say, training batch, or say any training epoch, which makes it you then what happens is that you try to make the information capturing mechanism much more redundant. So even if one of your nodes is failing to identify an information due to some reason, you have other nodes or neurons that can still capture the same information, and as a result you're making it much more robust and less reliant on maybe a particular neuron. Okay. That's the general idea behind your dropout. And in doing so, you're making the network be able to learn much more robust features, which are not easily affected by, say, positions or some sort of noise or some other factor that can maybe be present in your, say, given image or given input. And what happened after that was that since dropout, you're deleting an entire, say, neuron, and what happens is then associated all the inputs that are associated with that particular neuron, all of them have no contribution to the output. So a safer method was found out, which is drop connect, which instead of deleting an entire neuron would delete individual connections from, say, between two set of layers, instead of deleting an entire neuron. And that was sort of, you can say, useful if you have, say, already, if you already have, say, in general, when you're using a dropout inside your network, you'll observe that the generalization performance of that particular network improves very well. And when do you face a problem with generalization? When you generally may not have, say, enough data, even though this will work for larger amount of data as well. But if you don't have enough data in your training set, you tend to overfit to the given data. And when you overfit, your testing performance or generalization performance becomes very poor. Okay. But suppose if you already have a very small model and you start deleting individual nodes altogether in a neuron, then you're reducing the amount of learnable parameters by a very large extent for a small network. Okay. So that's where your drop connect comes into play, where it's a generalized version of dropout, where instead of dropping activations or entire output of a given neuron, it randomly drops some of the weights between the neurons or connections between the neurons. Okay. So if you look at this particular expression, uh, you have the original network which produces an output in this way. You have a W instead of WX, you have WV, and you have an A activation on top of it. So that's how you get the output. For your dropout network, you have a multiplication factor that gets multiplied to the output of every neuron. So it can make the entire neuron as zero if it wants to during testing or during training. But for your drop connect setup, this multiplication factor gets actually multiplied to the actual weight. So individual regions in your weight. So if you suppose you have a your layer that converts input of size 10 into inputs of size 20, so you have actually a weight of size 10 cross 20. So you will take this, say, 10 cross, you have 200 positions. So maybe some of the positions will be zeroed out by the drop connect network, instead of, say, maybe deleting one entire. If you delete out a dropout, if you use a dropout network, you may be removing maybe at a time 20 1 cross 20 connections. Maybe you have so you have say 20 neurons, so you'll be dropping 1 plus 20 connections at a time. But in case of drop connect, you'll be only maybe deleting maybe 1 or 2 weights in between or somewhere like
This means
that. Way you're
like,
not reducing the parameters too much. Yes.
या लाइक इन बीच वाले नोड में 4 इनपुट्स आ रहे हैं, तो उसमें से एक इनपुट मैंने डिलीट कर दिया, सो दिस इज ड्रॉप कनेक्ट, राइट? एंड रेस्ट नेटवर्क विल बी सप्लाई देयर फीड
Yeah,
फॉरवर्ड.
yeah, yeah. Exactly. That's the basic idea. Otherwise, in dropout network, what will happen is you will delete this entire set. So that way, it's not a very. I mean, for a small network, if you remove that much of a computation or parameters, you'll not be able to learn from it.
ओके.
So that's the idea behind it. Right. So that's the idea. Okay. So with this, we'll now move on to the next phase of representation learning. We'll be coming across a lot of topics today. So, I mean, we can have doubt clearing sessions based on them as well. But we'll be looking at a lot of topics today. So please listen to these things carefully. The next concept that comes up is the concept of transfer learning. As the name suggests, you want to transfer some information from maybe one task to another task, or maybe one model to another task and model, and we'll see why this may be necessary. Okay. So in certain situations, it might so happen that you want to perform a particular task. Maybe the task is still classification, but you are performing a classification on, say, cars. Okay. You have a classification for cars, or maybe you have a classification for trucks. And what turns out is you don't have that many label data for trucks. I mean, you have, say, 10 or 15 types of trucks, and ideally for training a deep learning model, you'll require a sizable quantity of images for training such a model. You will at least need, say, 100 if you want to get a good model that performs well on all tasks, all kinds of classes. So 100 images maybe per task. But maybe you only have, say, 10, 15 images per type class of trucks. And as a result, if you train a model directly on this particular task, your model performance will not be very high. So you find out suddenly that you may not have enough information for trucks, but maybe you have, say, a larger set of training samples for another task, which is maybe classification of cars. That's the idea. You have sufficient label for another task, say T1. Okay. And the data that is available for T1 is somewhat similar to the data that is available for T2. So both of them are vehicles. So both of them have, say, they'll have wheels, they have some idea of doors, something similar. So you have some similar, at least, vectors of variation in both these cases. So in such a case, transfer learning actually provides you an idea of transferring a model that is trained on, say, task T1, and using the representation that you have learned for T1 in order to improve the performance on T2. Okay, and this is the general idea of transfer learning, and we'll see a lot of versions of this, a lot of flavors of transfer learning, and the general idea roughly remains the same. You have data available for some larger set of classes for which you have large set of information, and you have another set of classes for which you don't have enough information, and you want to transfer the at least the representation learned from the initial set to the later set, or the initial task to the later task. That's the general idea of transfer learning, and this has been found to be very effective actually. And in fact, this is something that we have not borrowed it from somewhere else. It's something we always, as humans, we have been doing from a very long time. In fact, I mean, this, if you look at this example, if I already know how to identify all the cats that you generally see in India, and if I suddenly show you a Sphinx cat which does not have any fur, looking at just a single image, I'll be able to now identify any further Sphinx cat. You'll not have to look at 10 or 15 images of a Sphinx cat, then identify whether or what a Sphinx cat looks like, or what some foreign species of cat looks like. Okay. That's how, I mean, you're transferring knowledge from some previously existing model in your mind, maybe, into a new task of identifying a special class of a special breed of cats. Okay. And obviously, whenever we are doing transfer learning, the core assumption is that even though the tasks may be different, many of the factors of variations will have to be relevant. For I mean, factors of variation of the data for one task should be relevant for the data available for the other tasks as well. So if I have a set of trucks and I have another set of say fish or say a set of birds, that might not be able to improve my performance on trucks that much because you have a totally different type of representation. It will still improve because whenever you're dealing with images, um, you train a model on images. The at least as you know, the initial layers learns to identify edges, corners, contours, and all those things. So at least those features can be transferred to any other image as well. I mean, so that way it will be able to help out at least to some extent. But in some cases, if the features are too different or the domain itself is too different, transfer learning will not be able to help out in such cases. Okay, and there are various flavors of transfer learning. You have multitask learning, you have few shot and zero shot learning, you have incremental learning, and we'll see some examples of all of these flavors of transfer learning. Yes, I think someone is asking a question. Yes, Zagam Alicia. Okay, I think that's
Sorry, sir,
registered.
that was by mistake.
Okay, Chandramohan. Yes,
Okay, sir. Sir, in our organization, we are using transport learning technology.
I'm not able to hear you clearly.
Okay, okay. Okay, just wait for a second.
Okay, I'll get back to you. I'll just continue. Okay, and this is the concept of very basic example of say transfer learning, where you have basically, I mean, in fact, whenever you have tried to do some sort of model training and you have tried to look out for examples for this thing, you would have noticed, say, especially say if you have done a PyTorch based model training, you can actually fetch existing models like ResNet 18, ResNet 32, or ResNet 50 from Torch Vision. And there's an option to actually have these models as pre-trained. And when you say pre-trained models, these pre-trained models are actually referring to these models being trained, already trained on another image set that is known as the ImageNet data set, which is a very large data set. And that helps you to learn a lot of useful representation features, at least for natural images. And then if you have a target domain where you may not have that much data, in fact, if you even if you ignore say Pascal generally has large data set. But suppose you want to create your own data set using say some household items, or say all the people in your colony, you want to create a face classifier for those. ImageNet model generally provides a very good representation for you to then work on. So we'll see how to perform transfer learning, but the general idea is that you will train a source model on a source data set, which may be comparatively larger as compared to your given data set. I mean, this the whole point of performing transfer learning is that you don't have enough data on your target data set. And once you perform training on ImageNet, you then transfer this in knowledge that you have gained through ImageNet into the target model. Yes. Yes, Chandra. Yes, Chandra, you were saying something. Uh,
Chandra, you are on mute.
Hello, is my voice is audible?
yes, yes.
Okay. So, sir, in our organization, we are using transfer learning in some kind of defect detection. If there is any benchmark, so right now we have taken global data of at least 6 to 7 million of the images or the videos. So, if there is any benchmark that what is the stage when we will use the transfer learning, or how many
So,
images?
I mean, generally, you are saying for how to identify a situation where you require a transfer learning, right?
Yes.
So the thing is that first of all, if you have enough data for
Yes.
your specific setup, so you're doing defect detection. Maybe if you're doing defect detection in a sewage system,
Yes.
you might not have that much. If you don't have enough data for,
Mm-hmm.
say, a sewage system with defect detection, you will
Mm-hmm.
maybe take, say, a pre-trained object detection model that is able to identify cracks maybe in buildings,
Sure.
and then you fine tune it on your given say limited data set that you have. Okay. But
Okay.
suppose if you already have a lot of data set, I mean, you will get this idea of whether you're limited by the data or not when you're training your model. When you're training a model, if you and you keep aside say a portion of your data as a test set,
Mhm.
and if you observe that your model, when you're training a model and your training loss goes down and your test loss goes down to a specific level and it does not goes down any further, and the accuracy that you're achieving in your testing environment is not satisfactory for you, that is a indication that maybe you don't have enough data, or maybe the another factor can be that maybe your model is not complicated enough yet. So these are situations where you will explore maybe if there is another data set from where I can perform transfer learning, or maybe if there's a better model for this given purpose. So these are indicators when you're observing say, some sort of testing accuracy on your given set, and that is not satisfactory for you. You will try to maybe explore either more data, or maybe if you don't have more data, you try to then transfer knowledge from some other area.
Okay.
So
But sir, like,
for example, like Ultralytics or YOLO, they are trading they are every 6 months they are giving they are coming up with new version, either YOLO 8 or YOLO 9.
Yeah.
So what we had one discussion with their R&D team that they are using the transfer learning in releasing the new version. So sometimes it become a benchmark. We are using YOLO version 8, but at the time
Uh,
of release of the project, YOLO version 9 is there. So there are some kind of discussions with our customer that why you are not using the latest model. So
no.
they,
See, customer management is a different thing, but that is obviously whenever new version comes out,
yes,
it does not. I mean, it's not always be the case that for your specific task there will be a very large improvement with every version of you.
okay,
If there is a large improvement, you will do it in the next situation. But
okay,
obviously, I mean that's industry speak. I mean, you're more acquainted with those setups. I mean, your
okay,
customer cannot also change the requirement at the last moment, right? Or there is you ask the customer to pay for that changes. So that is something at a managerial level that you have to deal with. Obviously, it's not possible to come up with the best setup.
okay. Sir. Thank you, sir.
Yes, Anindya, you were asking something.
Yes. So basically, in transfer learning on a larger data set, we are specializing on means in each means means are we means only a we are transferring only a small set of learning which we thought that this got expert means uh, at an expert level so that we can able to transfer it to the smaller model and it can able to do much better job. Is that is what we are doing?
See, first of all, generally you perform transfer learning where the tasks are different in some way. The tasks are different in the sense that suppose just with the example I gave you that I have a classifier for cars and I have a classifier for trucks. But for the trucks classifier, I don't have enough data to train. Okay, so but for the car classifier, I have enough data for training it. So if I directly train my network on the trucks classifier, on the trucks data, maybe there is a very high chance that I'll overfit to the limited data and my performance will not be satisfactory. So what you're doing is that you're learning a much more general representation using a larger classifier or maybe a larger data. Network may be the same. You're learning a much more general or a better model for a car classifier. And as you already know, the initial layers, and we'll also see which layers we generally tend to pick up. The initial layers will be having much more generic features like say edges, corners, and that are not specific to say cars or maybe it's not specific to trucks. So these are features that you can, these are layers that you can directly utilize for your other network.
but sir, like totally opposite data cannot used, right? Like
Exactly, exactly,
if we are have
exactly.
a Apple data set, larger Apple data set, and we are try to predict the truck, it is not
Uh-huh.
possible.
So what will happen is that you may get some improvement still even there because both of them are images, both of them might have some edges and corners. So if you only pick the very initial layers and only use those for transforming information, we'll see how to transfer information in these cases. then maybe there will be some positives, but in general, you'll not get that much advantage of, using a Apple classifier and transferring the knowledge to a truck classifier. Okay.
So kind of like here we transferring the weights, right?
Yeah, I'll show what kind of how can you. There are many ways of transferring this information. We'll be covering those things in the next set of slides.
Oh,
So, once we do the transfer learning, say between car and trucks, then we cannot classify between car and trucks, right? I mean,
Yeah, that's an example that I'm providing. Suppose your objective is only to cover different types of trucks, okay, but you don't have enough data for that. So you're taking another data, you're taking another model and transferring that information here, so that you're able to extract better features. And finally, you'll classify trucks only because that was your objective. If your objective was to classify both cars and trucks, you would have used some other data.
right, got it.
Okay, sir. So idea is to take the initial layers from the very highly trained model, and on the
Yeah,
top of that, we will add few more layers to.
exactly.
You
That
know,
is one way. That is one way of doing transfer. There are also
Okay.
other approaches.
Okay.
But that is definitely one way of doing transfer.
Okay.
Okay. Okay. Yeah. So this is the first way and the most basic way of performing transfer learning, as someone had suggested as well. You train a network on, say, a larger data sets like ImageNet, and what you do is that you will basically remove everything after, from the classification layer onwards, and take the rest. Okay. And what you'll end up doing is you will directly use this region as your feature extract. Okay. And for now, we are not doing any training for this particular region. This region is directly taken from the source domain model. And what we'll end up doing is that in your target domain, you'll pass the limited training data, whatever you have for that domain, and you'll extract the features from there. And you'll only train a very shallow classifier, maybe a one layer fully connected network, or you can use some traditional ML techniques like, say, SVM and others, a logistic regression or whatever. And so what will happen is that you're fully dependent on the source domain's initial part of the network, which excludes the classification layer, in order to perform the classification for your target domain. Okay, that's a very basic way of performing transfer learning, and you might have observed this in many situations as well. If you have explored a bit about transfer learning, you would have observed some situations like this. But this is obviously not a well-tailored version for every situation, because you might require to further tune, at least to some degree, all of these layers as well. Okay, otherwise you might not get that much of an improvement in performance. So this is the general setup. One basic way of transfer learning: you will take the feature, you will take the a portion of your network that is trained on the source data, and you'll remove the classification layer of that particular network, and the rest of the network now acts as a generic feature extractor. And in your target domain, you will use this feature extract to extract features from the data and train a shallow network on top of those features. And that becomes your new classifier for your target data. And this will be, you will see that in some of the settings, like, say, in few shot learning and other settings. This is a very usual technique that is regularly used, where you don't have an option of training a new model if you have very less data. Okay, so you rely fully on the initial network for your features, and then you train a very shallow classifier. And if you have maybe enough data, you may try to even fine-tune this entire setup on the target data as well. Okay. So both of these options are available, and this is the most basic way of performing transfer learning, and you will see some of the other modifications of these approaches in the following different flavors of transfer learning as well.
So fine-tuning is basically when we take the, transfer the embeddings, convolution, and the model up until the classification point, and then we train it on the limited data.
So when we, in general, when you say fine tuning, you actually will not use a very high learning rate in general. Okay. So suppose if you train a model from scratch, you will maybe start with, say, if you're doing an HGT optimizer, you will start from a learning rate of 0.1. Then after some time, you reduce it to 0.01 and so on. But for fine tuning, the general idea is that the model is roughly performing good. So I'll not train it with a very, very high learning rate. I'll maybe train it with 0.01 learning rate and for a few epochs. Because anyways, if I train it for a very high learning rate, what will happen is that all of these learned information will get lost quickly. And in any case, we don't have enough data here. And so we'll start suffering from the same problem of overfitting again if you use a very high learning. Is that the doubt or something else?
Right. I mean, I think that clarifies that point. And the first part was basically we just pick it up as is and freeze
As
it.
is, yeah.
Right?
We freeze it, yeah. Yeah, these are the two options. Either you keep it frozen and train a very single layer, fully connected layer on top of it, classification layer on top of it, or a SVM on top of it, or you add a classification layer, but you do a very for a few epochs you perform some fine tuning.
And we utilize some gradients and all also, or just the weights? I mean, we just take the weights while doing the transfer, or we start
Only
from the
you basically just imagine you have just trained a model. Okay, what you do is that you simply delete the last layer, and that becomes your feature extractor now. So if you delete the last layer, what you will get is not, because if you had the last layer, you would have gotten, say for ImageNet, you would have gotten a 1000 dimension output, because that is corresponding to 1000 classes in ImageNet. So you exclude that, and you maybe at the previous layer you get a feature of size 512, and that you pass on the entire thing to your new network. So whatever new image you put to it, this will act like a black box and provide you a 512 dimension representation of feature. And based on that 512 dimension representation, that becomes a placeholder for your input. You train a shallow classifier.
Okay. Fine, sir. Thank you.
Okay. So, okay, right. As already mentioned by some other students as well, that if the source data and the target data are not related to each other, in some cases, the transfer learning may even hurt the performance, and in such cases, we call it a negative transfer. Okay, so we have to be careful about which data we are picking up for our purposes. Okay, great. So the one of the flavors of transfer learning is few shot learning. Okay, and this takes transfer learning to one of the extremities. It will take it to a level where a new task has very few training examples. So you have, suppose, a situation where you come up with a new task and you have, say, 5 classes, and each class only has 5 examples. And I ask you to now train a model on this. Obviously, if I now try to train, say, a fully connected network, even if I use a single layer fully connected network, what will end up happening is that that network will overfit to these 5 examples. And when you perform testing for these 5 examples, if your test examples do not contain these 5 examples that you have, your performance will be very poor, because your model has learned only to look at these 5 samples, and these 5 samples will fetch a good accuracy, but any other samples will not get a good performance from the model. Okay, so this is a very tricky situation, and few shot learning actually deals with such cases. Okay. Now, in this particular setup, we'll describe the settings first, and then we'll come to the solution. You have 2 types of classes. You have the base classes and the novel classes, and your base classes have large number of training samples. Okay, sounds similar to your standard transfer learning setting. And you have novel classes, which I just mentioned, which are generally will be provided to in the form of task, and also it's also known as an episode. So a novel class episode will be n-way k-shot, which means it will have n classes and k training samples per class. So we have k training samples, which is also known as support samples within the few shot domain, for each of the n novel classes. And these novel classes have not been seen by you during the base training phase. So these are absolutely new classes for you, and you're only provided with very few k support samples or trace signing samples. You can also have, say, a one-shot setting where k is actually 1. And the objective is to learn a good classifier for these n novel classes using only this k samples, which is a very difficult task. And if you look at any of the research literature of few shot learning, you'll see that no one tries to learn a new classifier based on only these 5 samples. Okay, because you're guaranteed to overfit to these 5 samples otherwise. So we'll try to solve this problem using few shot learning. And the episode that is provided also has some test samples, which are also known as query samples, on which you can directly evaluate your given model. Okay. Right? It is a difficult problem setting in general because of this limitation. So if the problem that lies over here is that if you try to train any model, you are guaranteed to overfit and perform only on the query images. Because query images definitely not be same as your support examples. So what can we do to solve this problem? And obviously we are in the paradigm of transfer learning. We'll do some sort of paradigm transfer learning only. And because we already know that we have a set of base classes for which we have enough data, okay, we'll try to transfer the knowledge of the base classes somehow into this particular set. And in fact, the approach that I will discuss has already in a way covered in the most basic way of transfer learning that we just discussed in the previous slide. So the solution idea will be that we will train a model on the base classes and transfer this knowledge somehow to the novel classes and be able to come up with a classifier. So we'll look at a very famous paper in few shot learning, even though it's not the initial paper. Initial paper was, I think, Samis networks. But prototypical network is a very famous paper in few shot learning, and it's still relevant to date. I mean, it's because of its effectiveness and its simplicity. Okay, and it uses a very basic version of transfer learning. So in prototypical network, your approach will be to first, and we'll come to why it's called a prototypical network at a later stage. So in prototypical network, what we'll do is that we'll try to first train a network on the base classes. Okay. Once you do that, you're done with the base classes. The classification layer is not useful for you anymore because you don't have that many classes in your novel task. So you'll discard the classification layer, and now we'll use this particular network as a feature extract, just like we were doing in the basic transfer learning setup. Okay. Now, with this particular feature extractor, it is not possible to fine tune it on the limited data available for the novel classes because we have so limited data. Otherwise, it will overfit and the performance will be gone. So how do we build a classifier for this particular setup? Remember, we have already seen this particular setup where you have a feature extractor that you cannot fine tune, and the option that you have over there is to come up with a very simple classifier on top of it. Okay. But the situation is such that even if you add a single fully connected layer, even that might overfit to your 5 classes that you have. Okay. So prototypical network, the authors of prototypical network came up with a very unique but very intuitive solution, all which is basically creating prototypes of the classes. Okay. What is a prototype? Prototype is a representative sample of a given class. Say, if I tell you that all sedan cars generally looks in a particular way. They will have a small bump at the end, and they will have a longer, say, front section. So that is how I'm describing a prototype for any sedan cars. And that's the general idea behind prototypes as well. Okay. So you take any class, if I can define a prototype or a rough image of how a rough feature that describes how a generic image from that particular class looks like, then I can use that particular prototype in order to create a classifier. How we'll create a classifier, we'll come to that. But the idea is to create prototypes for each class, each of the novel classes, and that's why it's also known as a prototypical network. So in order to create prototypes, what we do is that you have support samples, say K support samples for each of the novel classes in your given episode. You extract the features from using the feature extractor from the samples, and you take the average of the support sample features. Okay? So it will be support sample features. Once you take the average of the support sample features, in the feature space, you can look at something like this. You had the individual, say, features of a given class, you take the average, you come up with some average feature like this. Okay. And then the task becomes actually very straightforward. You have the average feature. Now what you do is that you will say, given any say query image, you will extract the feature using the same feature extractor, and you will get say feature somewhere say in the feature space in this way. Okay. So you have one feature of the query image, and you have, say if you have three classes, you have three prototypes. You simply find out which prototype is your current feature closest to. Okay, you take the distance, you calculate the distance between this pairwise, say between Z and C1, Z and C2, Z and C3, and you find out which is the closest, and that is basically your predicted class. Okay. And this is basically the idea behind protocol. There's nothing complicated about this. So you take Z, you find the distance. Suppose you have a five-way case, you have five classes. So you have also identified the five prototypes of each of these classes by averaging the features of those classes. You find the distance, and suppose the distance are d1 to d5, and you basically come up with a probability for every class. Probability that Z belongs to a particular class. And how do you do that? It's simply, if you can look at it, it's an exponent of the negative distance of that class divided by the summation of the negative distance of all classes. Okay. Now, if you look at it, for now, just ignore the exponent part. If I only consider the negative distance for simplicity, and then I consider all your other distances. Okay. What will happen is, this will give me a ratio, or this will give me a ratio of the contribution of that distance to the total distance, right? You have the total distance at the bottom, and you have the class for which you want to find out the prediction probability on top. So if I get a ratio, if one of the classes, if the class has the highest ratio of contribution to this total distance, okay, then that class will be my predicted class. Remember, these are all negative distances. And we'll come to that as well, why you're using a negative distance. So with this, whichever class gets the highest probability is basically the class to which this particular Z feature is the closest to, and that will be my predicted class. And that's the basic idea behind prototypical network. Okay. Now, can anyone say why am I using the negative distance rather than the positive distance?
We want to minimum distance. We want to find
Yes,
out.
exactly.
But
Exactly.
sir,
So
to calculate that also, we can take reciprocal of distance also, right? Is it feasible?
you can take reciprocal of distance. Okay. I mean, for reciprocal, whichever is the highest, in that case will be, I mean, we actually has the lowest distance. So that will also go. That's true. That's fine. So that's the idea. I mean, you take the distances and you get through this expression the class for which, I mean, the probability for each of the classes, and the class for which the distance is the lowest, you will get the highest probability for that particular situation.
This is like similar to the KNN, right? Nearest node.
Yeah, exactly. So you're performing sort of K nearest neighbors, and in this case, K is the number of class prototypes that you have.
And so, like, what is difference between that KNN and this short
Wait.
learning?
Not KNN, because K nearest neighbor is different. K nearest neighbor is, it will find the distance from all the samples and then choose the top K samples. Okay, that way K nearest neighbor is different. So what K nearest neighbor does, if you have say 20 samples and you take one test image, you find distances with all these 20 samples, and then you find say the top 5 samples which this is closest to, and among these top 5 samples you will see the classes, and whichever classes is majority in that 5 samples, that will be your predicted class. Okay, but in this case you only take the distance from the 5 or the prototypes that you have, only the 5 prototypes that you have, and one of them will be your predicted class. There is no concept of majority or say multiple contributions from the same class. That way it's different. Okay. So in this particular setup, what I described to you was that you have trained the base network or the base task, the base classes in its usual manner, But actually, the original paper suggested to also train the base network also in terms of episodes, so that you can match the base classes with the novel class. So you also convert these base classes into episodes containing, say, 5-way 5 short, and then you train the network. But in later research papers, it was found out that it's better to simply train the base class in the general, say, batch-wise manner, how you train a general network on a given training data, and then you use that feature extractor and perform classification on your novel tasks. Okay, this idea is clear about prototypical networks. This is a very straightforward and very efficient sort of, a very simple sort of a method. There's nothing complicated much about it. That's this way of, yeah. I think someone is asking a question.
Sir, I understood the concept, but I was not able to understand the finally how we are getting the the which is the final class, right, for our new.
So yeah, okay. So you have your feature Z, and you have all of these class prototypes. Okay. Ignore this equation for now. Your prediction is basically whichever prototype is closest to you, that class will be your predicted class. Is that portion clear, please?
Yes, sir.
Huh. So in order to find that, you'll not either you can directly find the shortest distance and come up with the and directly show the predicted class, or if you want a class-wise probability, okay, that is where this expression comes into play. You're dividing basically the negative contribution of the distance from that class with the total negative distances of all the classes. So that way you're taking up a ratio of contributions, right? So if the total distance from all the classes, say this class contributes 10, this class contributes 20, this class contributes 5. So if you have, say, -10, -20, and -5, the one where you have -5 will effectively, so first of all, this whole minus will get cancelled. You have, say, 5 by, say, how much is it? 35. Actually, just a second. Acha, these are, I think, in terms of, that's why we also need an exponent. But just a second. The idea is still the same. You want to find the contribution of any given, say, prototype into finding out the probability of that particular class for that given sample. So what you end up doing is that if you take an exponent of the negative distance, okay, this value will be compared, if this value is small, or this value will end up increasing the value of, this value, overall value will be higher as compared to the other values. I may not be able to clearly explain it, but if you take a set of distances and place it basically in this equation, you can try it on your own as well. If you take a set of distances and place it in this particular equation, the distance for the class for which distance is the lowest will give you the highest value from this particular equation. And we are calling it as the probability for that given class. So the class which has the highest probability is indirectly the class which has the lowest distance from the given Z, or this given feature of your query image. And that's how you'll be able to identify which is your predicted class. Okay. If it is still not clear, you can just maybe try a set of values ranging from, say 5 to, say, 25 and all, and place it in that equation, and you will see that the one where you have lower distance will get a higher probability.
Yes, okay. Correct.
So we will calculate this Py equal to C1 for all the classes, right? C2, C3, C4.
Yes, C1, C2, C3, C4, C5.
Okay, got it.
Okay, that way you'll get the probability.
So one general question, it's a called few spot because it's a very few data, right? Spot means yes. Data image like that.
Yes. Right. Yeah. So this, as I've already mentioned, this was found to be extremely effective, and it was also beating at least the state-of-the-art methods in those days. And those methods were actually using a lot of complicated setup. They were actually using an LSTM to sequentially learn a new model and all for training, for evaluating the novel classes. And this was able to beat all of those by using a simple average prototype for all these cases. And this actually demonstrates the power of good representation learning. If you're performing a good, if your representation learning is good, you're able to extend it or transfer this knowledge to a different target domain where you may not have that much data, but you have you're still able to perform well on this sequence. Okay. The next setup that we'll briefly cover and that will be the last topic we cover for today, is the usual extension of, say, few shot learning. You had a setup where you had few data. What if now you have no data for some of the classes? So if you consider this particular example, you will see that for auto, horse, and dog, you have a large number of training samples. Okay. However, for these classes of truck and cat, you don't have any training sample. Okay. Then in such a situation, I want to develop a classifier for truck and cat without having access to any training data or training images from truck and cat. This seems far-fetched, but actually it's a very useful, one useful side effect of having transfer learning. That good side effect of using, say, transfer learning. So zero-shot learning is another extreme form of transfer learning where the new tasks have no training samples. And obviously in such case, it becomes, directly, it's not directly evident how you will solve such a problem. Even in this case, you will have a set of two disjoint classes. You will have seen classes and unseen classes. And as the name suggests, seen classes are ones for which you have training samples, and unseen classes are those for which you do not have any training samples. That way, it's a very interesting setup. Okay. And the paste class obviously involves learning to classify the seen classes, and we'll do some sort of transfer learning in order to learn the unseen classes as well. Okay. And the seen classes have a large number of training samples. The unseen task in this case obviously now involves classifying these unseen novel classes. Okay. But the difference from few shot learning is that you don't even have the few support examples over here. Okay. You have two type of setups within zero-shot learning. You have a standard zero-shot learning setup where the model is solely judged on its classification accuracy on the unseen classes. Okay, which is maybe comparatively easier. You will transfer the knowledge from your base classes and maybe update the model a bit, but you'll not bother about what happened, whether this model can still perform well on your base classes or not. And then you have a much more realistic generalized zero-shot learning setup where you have to take care of the accuracies of both the seen and unseen classes. You cannot destroy the performance on the seen classes just for the sake of improving the performance on the unseen classes. Okay. These are the two setups for this. Okay. And the objective obviously is to learn a good classifier for unseen classes for a general zero-shot learning setup, and also the seen classes for a generalized zero-shot learning setup. Right. So the obvious problem is, if you don't have a any training data for a class, how will you predict the class for such sample from testing sample from such a class? You will not be able to do so. Suppose if I have only trained a model on auto, horse, and dog, the prediction can either be auto or horse or dog. Even if you provide a truck image or a cat image, it will give you one of these as a prediction. Maybe the confidence will be much low, but the prediction will be auto, horse, or dog. So how do you deal with such a situation? So we'll come up with a solution idea, and it was a very unique way of solving this particular setup, which actually involved language for the first time. So you had an image-based problem, and you'll try to solve this problem because there was no image available for you. We'll try to solve the problem from a language or semantic perspective. What is the one thing that we have about all the classes? We have the class names for all the classes. Okay, and we already have enough literature where you have word embeddings such that if you pick word embeddings of similar classes, these word embeddings will be close to each other in the semantic embedding space, and if two words are dissimilar, they will be far away from each other in the semantic embedding space, and that is the basic solution idea. Okay, so since only the seen classes contain training images, we can learn an image feature space containing only the on only the seen classes. Okay, and then what we can do is that we can use the word embeddings or attribute embeddings. This word or embeddings or attribute will come from the classes that you're dealing with. and we'll try to, and that is something we have for both the seen and unseen classes, and we'll try to build a common semantic space, okay, for these sort of semantic embeddings. And once you have your semantic embedding space and your image feature space, we'll try to learn a mapping between. So we'll try to learn a common feature space where if you pick any feature that is similar in terms of, I mean, similar images will be close to each other in that embedding space, as well as similar text will be close to each other in that common embedding space. So you are learning two different modalities, one based on images, one based on text embeddings, and you're learning a common embedding utilizing both of these feature spaces. And that way you will be now able to transfer the image features information or the image representation information onto your zero shot classes as well, or the unseen classes as well. It seems far-fetched, but once we describe the actual method, it will become much more clear. Okay, so we'll discuss one very popular approach of zero shot learning, which is also known as CADA VAE. Remember, in VAE, A is still autoencoder. VAE is a variational autoencoder that's a generative model. We'll look into generative model in the third fractal, so that will come later on. I'll just briefly cover the idea behind that so that you can at least follow up on this topic. So, CADA VAE, what it does is that it learns latent embeddings or some embeddings of image features, and it learns class embeddings from the class labels of all the classes. Okay, and when you say class labels of all the classes, you're utilizing the class labels of unseen classes as well. Okay. And you're utilizing basically a specialized form of an autoencoder. This is a very variational autoencoder in order to learn these embeddings. Okay, and we'll also learn a mapping between these embeddings, and this mapping will be learned by using a cross alignment loss, and we'll see what these actually mean. But the general idea is that you have two variational autoencoders. One of the variational autoencoder will be for images. One of them will be for text or the semantic embeddings. And autoencoder, when you say autoencoder, you have an encoder as well as a decoder. So it's not that you're only looking at the encoder. You have the encoder and the decoder. And the variational autoencoder, we'll briefly look into that, and but because it will come up later, so we'll not go into too much depth of variation autoencoder. Okay. So for now, you assume that variational autoencoder is a special type of an autoencoder that can generate multiple related embeddings from the same input. So when you have studied, say, an encoder, autoencoder, you would have noticed that I provide some input here and I get back an output over here, and I get a single embedding that represents this particular input, a compressed version of X as an output of the encoder, right? What VAE does is, VAE, while performing, the encoder of VAE produces two things. It produces a mean embedding and a variation, okay, or say standard deviation. And what you end up doing is, there is a property of your Gaussian distribution where if I give you a mean and a variance, I'll be able to generate more features that satisfy a Gaussian distribution with the same mean and same variance. So that is the core idea behind a generative model based VAE. Instead of generating a single embedding, a compressed version, you create a mean embedding and a variance. And using this mean and variance, you can create multiple embeddings. Okay. And these all embeddings becomes useful when you have, say, very less data. You can create multiple embeddings from the same image. Okay, and this will not necessarily be the same embedding multiple times. They will have some variations among them as well. So the variation autoencoder actually learns some factors of variation within the images and is able to generate multiple features or multiple embeddings from the same image. That's the basic idea behind a VAE. For further, we'll look into that once we come to generative modeling. Okay, so for now we have the setup of VAE. You have one special autoencoder for images, which can only train on the seen classes. And we have one special autoencoder for semantic data, which is some sort of word embeddings that you're obtaining for all of the class names or description of classes. Okay. So there are already a lot of language models. I mean, the basic one is word2vec. I think if some of you have worked with some NLP related tasks, you must have heard of word2vec. which is basically if you provide it with a word, it will give you a corresponding vector representation of that given word, and that vector representation will be these vector representations are just not describing the word itself; it also describes relationship between other words. So if you have two embeddings, if you have two words that are similar to each other in meaning or concepts, they will also be closer in this semantic feature space. And if two words are dissimilar or opposite of each other, they will be far away from each other in this particular feature space. Okay. And that will be the idea that we'll be using basically in order to perform this sort of zero-shot learning. Okay. And this particular special autoencoder can utilize both the seen and unseen classes, because you at least know the class names, even though you don't have the I mean, in this particular setup, you know at least the class names, but you don't have the images for your unseen classes.